In this session, we're going to discuss chilled beam control strategies. In particular, we're going to talk about constant airflow systems. So here's our basic system. We have an air handling unit that's providing the primary air through the supply air ductwork out to each one of the active chilled beams. In addition to the primary air that's delivered to the beams, you would also have chilled water and possibly hot water, depending on the system design. Now, this is a constant volume system, meaning that it is going to run at its design airflow rate whenever the system is in operation. This is usually controlled by the building automation system. If the building is going to start at 7 o'clock in the morning, at 7, the building automation system will start the unit up and it will run at its design airflow rate all during the operating hours until night's shutdown. And that allows you to use manual balancing dampers in the ductwork to make sure that the air is the right amount to each one of the beams. If these beams are all identical, you would use these manual balancing dampers to adjust the airflow rate to the beam that's closest to the air handling unit, but also make sure that you could deliver the right amount of air to the beam down here that's furthest from the air handling unit. So let's talk a little bit more about the air handling unit itself and its controls. So we said it was a constant volume system, so there's no adjustment to the airflow. That would be done during commissioning, and so unless there's a change in the design of the building, it will be either off or providing a constant airflow. Now, in a lot of chilled beam projects, you have some form of energy recovery unit, and in this case, this is a 100% outside air arrangement. It's very popular, but with an energy recovery device to do as much of the recover as much energy as you can in both the summer and the winter, and so the return air is passing through one way, and the outdoor air is being brought into the unit and then heated and cooled and delivered to the space. The unit itself is going to have discharge air temperature control. Its purpose in life is to deliver air at a fixed temperature, so it's often somewhere between 55 and 75 degrees. Again, it depends on the design. There's no right or wrong answer. And so there'll be some form of discharge air temperature sensor that will be controlling the energy recovery to maximize that, but also supplementing the energy recovery with heating and cooling. And because it's a chilled beam system and you typically have hot water and chilled water in the building, these are usually hydronic systems with chilled water and hot water coils in them to do the cooling and the dehumidification. Now, if you're going to be monitoring your humidity, which is very likely, you're also likely to have some form of humidistat in that air, and that may actually come back into the control sequence. In example, if you were doing dehumidification with reheat, you'd need to be monitoring the humidity as well as the temperature to make the right decisions about how to operate the coils. Now, another thing that you'll often see in a unit is that they'll add a recirculating section into the unit. So it's not unusual for a chilled beam system to supply more primary air to the building than the actual outdoor air requirement as per, say, ASHRAE standard 62.1. So in an office space, 62.1 is somewhere around 1.1 to 0.15 CFM a square foot. It's not unusual to see a chilled beam system designed at 0.3 CFM a square foot. So rather than bringing 100% outside air into the building, you may choose to recirculate some air through some form of mixing box. And if you do this, you're going to need a control sequence that makes sure that you deliver the prescribed amount of outside air. So either some kind of airflow station or some other control technology to make sure that you maintain your minimum outside air requirements to the space during occupied hours. Now, one of the nice things about having a recirculating section is during night setback. If the building cools down in the winter or heats up in the summer during the unoccupied hours, you need to consider how you might be able to add some extra heat to the zone that's outside of tolerance. So if you have a building automation system and it's monitoring all the control zones in the building, system shut down at night, fans are off, dampers are closed, without any air recirculating through a chilled beam, opening the hot water valve or the chilled water valve at the beam will not add any heat to that space or any cooling effect to that space. So if you have a recirculating section, you can do something like this, where during night setback, you leave the outside air dampers closed, you leave the exhaust air fan off, and then you just recirculate air through the unit. You normally would not heat or cool it. deliver it out to the space, and then whatever beams are in the zone that's either too hot or too cold, with some air flowing through them, you can now start to do some local heating and cooling in that space with the coils that are built into the chilled beam. So a nice thing to be able to do if you want to have either night setback or morning warm up or cool down as an option. So we talked about the air handling system and the controls in the air handling system. Let's start to zero in on a control zone. And the first thing we want to talk about is we shouldn't think of each chilled beam as being a control unit onto its own. You can mount unit controllers right on the chilled beam. You can have valves added right to the beam and treat one beam as a control zone, but it tends to be expensive. You can see that happening in, say, a private office where there's only one chilled beam in that space. That would make sense. But a better way to look at it is to divide the building up into control zones. And there will almost certainly be multiple beams within that control zone. And so there will be one unit controller from the building automation company that's servicing this. This box here would be our control zone. If it was a classroom, that would be very obvious. In an office space, an open office concept, this might be at least one of these 4 facades, and then maybe 1 or 2 in the core. And then if you had specialty spaces like conference rooms or private offices, they might also be control zones. Same rationale and logic you would use if you were dividing a building up for a VAV system. Now, once you have a control zone, you'll have one controller in that control zone, and it will treat all the beams the same. And so it will be monitoring the conditions in that space. We're going to talk through these different sequences here shortly, but it will be gathering data about that space and making decisions. And whatever decision it makes, it will get all the beams that service that zone to behave the same. So we have our primary air main duct here. You can see we're branching off. It's typically around 55 degrees, although it can be warmer. That's not a right or a wrong. And because this is a constant volume system, you're going to get design airflow rate all the time. And you can have manual balancing dampers in here to make sure that each beam gets the right amount of air. And you can see that the controller, not only is it monitoring at least the temperature and the dew point and maybe indoor air quality in that space, it is also wired to the hot water valve and the chilled water valve. And so it can, if it sees a demand, it can either add heat or add cooling effect to the space. So let's start with cooling. So here the blue line will be our chilled water line. It's coming over here, and we're going to start. You can see with this red line that right now, from a control point of view, this space is satisfied. It's in its deadband. It doesn't need heating. It doesn't need cooling. And so both valves are closed. This temperature sensor is reading the temperature of the space and comparing it to its set point, and it's inside the deadband. So this is neutral. And then we're going to have an increase in internal heat gain. And so you can see that we're no longer satisfying the space. The temperature has moved away from the set point, the deadband area. And so now what happens is the controller will start to modulate that chilled water valve to the beams and to meet that load. And it will be able to vary the flow rate through here to come up to a balance point and zero in on it. Now you'll notice that there's only one valve. This is a good recommendation to help manage the capital costs of the project, is to have one chilled water valve and one hot water valve for the whole control zone. And so that when this valve opens, it will actually let water go to all 4 beams. And if you needed hot water, it would also allow that hot water to go to all 4 beams. You don't want a situation where one beam is opening its chilled water valve and then the beam over here is opening its hot water valve. So there's an advantage in having one valve per control zone. So in this case, you can see how the system is going to respond. A typical flow rate for a chilled beam is about 1 GPM. So this is 4 GPM, and it's realistic that you could get a modulating valve that would have some level of rangeability, and so you'll be able to modulate that flow to meet the load. And if you look down here and you're going to provide 55 degree air, you should notice that the air can actually do some cooling effect in here. If we consider the y-axis here to be the amount of cooling capacity that the system is providing, as long as you're providing 55 degree air to the space, it will do some amount of cooling. And so what's happened as we've moved here is that the air isn't enough to meet the load, and so now we have to run some chilled water through the beams, and as you can see, the more flow we put through it, the more capacity we'll have to meet the load. Well, let's switch it around and see what happens when you go the other way. So now you can see this is what we would call a 4-pipe system. So you have hot water coil as well as a chilled water coil in each beam. So there will be 4 connections to the beam, just like a 4-pipe fan coil. And you can see that we have a hot water valve that the controller can manage. Again, a temperature sensor that is looking at the set point. And now you can see the hot water distribution system providing hot water available to all the chilled beams. And again, there's only going to be one hot water control valve per control zone. Typically, a chilled beam is closer to somewhere between 0.5 and 1 GPM of hot water. So this is going to be somewhere between 2 and 4 GPM for the zone that you see here with 4 beams in it. So now let's talk about what happens during the controls. So you can see down here, we are inside in the dead band, so this space is satisfied. It's not hot, it's not cold. The temperature that's being read is basically matching the set point, so the hot water valve would be closed. And then, of course, as the temperature drops in this space, it gets colder outside, or you have less internal heat gain, we're no longer in the set point, we're below set point. And so the controller will start to modulate this hot water valve to match the load requirements of the space. And so it'll be able to vary the flow. And as it does that, that flow will go to all 4 beams so that we get even heat all through this zone. And that will move that back up into to the dead band and satisfy the space. Now, a lot of people are very interested in how you manage dew point control in a space, and that comes around because chilled beams are sensible devices. There are no drain pans, there is no condensate piping to a chilled beam, and so their purpose in life is to either add sensible heat or remove sensible heat as required for the space. They are not capable of removing humidity. That actually gets done with the primary air. That primary air will be selected, its cyclometric conditions selected so that it will provide a drying effect in the space. Now this is a constant volume system, and so you're going to get full drying effect all the time, whether you need it or not. So whether it's a low humidity load in the space or a high humidity load, you'll have the design amount of primary air going into the space, and so you're going to have maximum drying effect. But what happens if something goes outside of expectations? An example would be that somebody has the doors propped open to the outside while they're moving furniture in or out, or you have some other event that's adding a lot of humidity to the space. What are we going to do about that? And so you tend to get 2 approaches. This is what I'm showing up here is some form of dew point sensor. It's actually on the coil inside the chilled beam, so as the air from the room is drawn through the chilled beam, it's actually being pulled across the sensor, so it's a good place to mount the sensor. It's out of sight, nobody would see it. The cover is off right now. Another approach that you'll see is a condensate sensor. Now this will have a pair of probes that are going to be in contact with typically with the supply side of the chilled water piping, and that's going to be probably the coldest thing in a control zone. And so if the humidity is too high in this air, this is going to be the first place where you're going to see condensate start to bead on this pipe. And if any water starts to form on this pipe, the sensor will pick that up and let the building automation system know that the condensation is starting to form. So the top one allows you to be more proactive. As you get close to your dew point, you can start looking at strategies to manage the fact that you're getting very close to dew point, which is when condensations start to form. The other one's a little bit more of a sensor that's around, it's more like closing the gate after the horses have left. This sensor is going to tell you you've already got condensate forming, so you don't really have time to react to it. You're going to be much more of I don't want to call it a crisis mode, but you're going to be much more pressed to respond quickly to the situation. It's kind of a high-level alarm. So there's a bunch of different ways you can do things to help manage dew point. So let's talk about a situation right now, and what we're going to do here is what's going on if the space is satisfied in terms of temperature. You can see we're modulating the cooling, we're meeting the load, but we have a dew point sensor right here, and it's monitoring the space. If you are below your dew point setting, which might be 80 or 90% dew point, then there's no change. You let the system do what it would normally do and heat and cool the space as you want. But what happens if we start to have the dew point start to climb in the space? And so the most common approach to deal with this thing is to close off the chilled water valve. It's the chilled water that's going to be the coldest thing in the room. It is what would cause the piping to sweat. It's what would cause the coils to sweat. And so the solution is, if something's gone unusually wrong in the space and you sense that, close off the water to this control zone. Now, this will solve the problem about whether or not these beams are going to sweat and start dripping on the floor, but you've also just turned off the air conditioning in a control zone that almost certainly needs air conditioning. So while it's protecting the building, it is not helping the occupants at all. And so it is a good, kind of crisis level backup system, but it is not going to satisfy the occupants of the space very well. So one of the other things you could look at doing would be a boost mode, and that would require some thought about how the air handling system was sized. But if you went back and had a little bit of extra capacity in your primary air handling system so that it could get to 110 or 120% of normal design airflow, you could use your dew point sensor to recognize when you might want to go into boost airflow mode. And so what would happen here is, in the same situation where we have an increase in the dew point and it's starting to get us in trouble, and the dew point sensor is showing that the dew point is being closely approached in the space, then what you do is use that signal to go back to the air handling unit and say, don't operate at design airflow rate, step up to 120% of design airflow, and that will drive air not just into this zone, but every zone that that air handling unit serves. And what that'll do for you is help dry the building out. So there's a couple of reasons that helps you. The first one is, remember that it's the primary air that is the drying source in the building. Its dew point was picked out of the air handling unit based on the design conditions of the building. So the more of that air you get to the space, the faster you're going to dry it out. And the other thing is, it's actually very hard to keep humidity trapped in one zone. I mean, we're only seeing one zone here, but if this was some kind of conference room, or they had open patio doors or allowed some way to get a lot of humidity in the space, that humidity will travel through this zone to the adjacent zones. And so as you open up this air handling system and start to dry out a larger area, it will help you get that humidity out of the building. So you can close this valve off so that you don't run a risk of condensation. Now you've got high humidity. What you want to do is to flush this area with as much air as possible to dry it out. So this will help as a backup plan to help deal with an unusual circumstance. The last one to look at is that we'll talk about is what about resetting the chilled water? The problem with just closing the valve and saying, okay, you can't have any chilled water because we don't want it to sweat, is we've now lost complete temperature control of the space. And so any occupant in the space is going to be dissatisfied very quickly. So a different way to look at doing this thing is to say, hey, we're going to monitor the dew point in the space. And if we start to get close to that dew point, what we're going to do is actually start to raise the chilled water loop temperature. Normally they're designed for around 57 degrees, but as you get closer and closer to dew point, you might reset that chilled water to 58 or 59. You will absolutely give up cooling capacity for all the chilled beams that are hooked to that water loop. That's the downside. The upside is we can keep modulating chilled water into all the zones to help try to manage the cooling effect in here until we can get the primary air to dry the space out. Now, to do that, you really need a dew point sensor as opposed to a condensate sensor. If you have a condensate sensor, you already have a condensation problem by the time that sensor's tripped. A dew point will warn you that you're heading in the wrong direction, that you're getting close to a condensation situation. And so that's why dew point sensors are considered a superior solution. So resetting the chilled water to stay above dew point is a legitimate control sequence to help manage a possible condensation situation. And normally we'd say try to stay 1 degree Fahrenheit above whatever the dew point is of the worst zone in the building. Now, we were talking about using dew point sensors at each one of the control zones. That's just going to end up with a lot of dew point sensors. Another way to do it would be to look at having dew point sensors, let's say typically per floor. And remember what we were talking about earlier, it's actually really hard to keep humidity in one space. So if each one of these was its own office or its own space, if you have a high humidity situation here, that humidity will quickly spread through the space across the whole floor, and so you can get away with having just one sensor per floor and monitor, using your building automation system, monitor the overall dew point of the building floor by floor. Or if you had a large building, you might put a couple of sensors per floor at strategic locations, and use these, that if any one of these things is getting close to the dew point limit, is to use that signal to reset the chilled water. So it's a nice way to be able to do that. And we would suggest that you only reset the chilled water to the loop that's going out to the chilled beams. Don't reset the temperature at the chiller because that will warm the water that's going to be going out to the air handling units, which is right now you need to keep cool so that you can dehumidify the building. So just do the loop that services the chilled beams. So another thing that you'll see commonly done here is, what if you're doing a more residential type space, might be a hotel or a dormitory or a retirement home, someplace that has windows, especially operable windows. And so you'll see that there'll be window switches added to those windows. And so instead of having a dew point sensor, you would have a window switch, and the moment that window is opened, you would turn off the chilled water valve and close it. And that makes sense. That doesn't. It's not a good idea to be running your air conditioning at the same time you're opening your windows. The occupant really needs to choose which way they want to do it. They have the best idea of what's going to make them the most comfortable in the space, and if they want the windows open, that's great. But we're going to shut the air conditioning system down until they close the windows. So the moment that window switch opens, then that would be the signal for the controller to shut off the chilled water valve. And remember that if they close that window, what you're going to get here is very quickly this primary air will dry the space out as it brings in air that's been conditioned and dehumidified, and your chilled water valve will be allowed to operate, and they'll be able to get mechanical air conditioning in the space. So that's a quick rundown about common ways of managing a constant volume chilled beam system, and the most common questions that come up that can be used for doing a control system. Thank you very much.